Great, it's exactly 11, so I guess I should start. Thank you all for coming, it's great to see you. I hope you've been enjoying the remarkably nice weather. It's been a busy period for me. I saw you last Saturday. On Sunday, I flew to Caltech to where I've been asked to give a seminar on some of my recent research with one of the brilliant professors here, Clay Cordova, that's been garnering a lot of interest, which has been fun. And then tomorrow I fly to Amherst, where I've also been asked to give a primer on this sort of research. Busy period, but I'm excited to be back here to be able to talk to you today because we're going to get down finally to the smallest scales we can yet understand to really probe the structure of ourselves, of matter, at scales of something like 10 to the minus 20 meters. So let me briefly remind you, maybe I should pause for a moment while we, good. Let me briefly remind you where we've been. We've been zooming down from human-sized scales to the smallest scales we can yet understand. A couple of weeks ago, we were at the atomic scale, something like 10 to the minus 10 meters, and we talked about quantum mechanics and about understanding the structure of the hydrogen atom made out of protons and electrons held together by photons. And then last week, we went down to the nuclear scale. We talked a bit about the electromagnetic field as being composed of photons. We saw that the nucleus itself is a collection of neutrons and protons, which are held together by these particles called pions. We observed the phenomenon of weak nuclear decays and found the neutrinos. And today we're going to go another few orders of magnitude down in scale and see the actual standard model of particle physics, our best theory yet for what physics looks like at fundamental scales. And I wanted to start just by briefly, I said the words quantum field last week, but I don't think I gave enough of an intuitive picture, so I wanted to briefly just play a sort of animation I found. When you imagine a field, you should think of some value at every point in space, and most of the time in vacuum, in the lowest energy state, these quantum fields have nothing in them. They're just around zero, although there are quantum fluctuations which are being animated here. But the particles that we've talked about, you should think of as some localized excitations of energy in these quantum fields. So this is showing, indeed, not only do we have a quantum field for the photon, like you can talk about a classical electromagnetic field, but really, and you can talk about photons as excitations of it, but really throughout all of space, there are quantum fields corresponding to each of our types of particles, like photons, electrons, quarks, and these exist throughout all of space. They can all be excited to pop out particle-antiparticle pairs out of the vacuum, and these different fields sort of interact with each other. So I just wanted to give, we'll talk a little bit more today about the language of fields, especially when we get to the Higgs, but I just wanted to play something to give you a bit of a picture of what to have in your mind. Great. Okay, but let's continue trying to understand what matter looks like at smaller and smaller scales. And of course, the way we're going to do this, as we have been, is, or I should say, the way really fantastic experimentalists did over the course of the 20th century, is by setting up scattering experiments, colliding particles at higher and higher energies. And of course, so last week, we found the nucleus is composed of protons and neutrons, and so now a very natural thing to do is we should try hitting those protons and neutrons with energetic other particles like electrons or like photons, and that leads to what was initially quite a surprise, that the proton and neutron themselves are not fundamental particles, but they are also composites. There were these, a great way to see this is that if you shoot some very energetic photons at a proton, you produce excited states of the proton, sort of excited versions of the proton and neutron. This is showing as a function of energy the peaks in this spectrum where you're measuring how often some scattering process happens corresponds to new excited versions of the proton and neutron. And the way you should think of this, the reason that this tells us that the proton and neutron are composites is just like we saw for hydrogen. Hydrogen is a bound state of a proton and an electron, and we saw that there was some ground state. We talked a bunch about how quantum mechanics gives this feature that that bound states come in sort of discrete amounts. You can have a hydrogen atom in its ground state, but you can also have a hydrogen atom in its excited state. This is, well, I don't even have to draw. Whoops. Gosh, there we go. Yeah, good. So we have some ground state of hydrogen where the proton and the electron interact in the least energetic way, but we know that the hydrogen can absorb a photon and be excited up to some higher energy way that the proton and the electron can interact. And indeed, this is a general feature of bound states in quantum mechanics. So the fact that we can observe some excited states of the proton and the neutron means that these two are composites. But they're composites in a very different and interesting sort of sense. We call the components of protons and neutrons and pions also quarks. And just like the hydrogen atom is a composite of the proton and the electron, which are held together by the electromagnetic force, by the photon, there is a new sort of force responsible for these composites. So I want to we have to revisit our notion of charge. And this is something that there have been some great questions about. We talked about last time that charge is a property of a particle, of a physical system, which tells you indeed how, electromagnetic charge tells you how your particles interact with the photon. Good, we talked about describing this with Feynman diagrams, explaining how by exchanging a photon between two different electrons, that's the quantum mechanical origin of the electromagnetic force that says that two electrons repel each other. Now, it turns out once you go to quantum field theory, this electromagnetic interaction is just the very simplest sort of quantum mechanical theory of a force that you can have. And simplest in a real sense, this is the reason why we could understand electromagnetism classically. We can talk about a classical theory of electromagnetism, but in general, we can't. And we need for this new force a new notion of charge. Let's see what I'd like to write. Well, if we haven't talked about gravity, and that will start in earnest next week when we switch gears to cosmology. But gravity is also carried by in the field theory description, carried by a massless boson known as the graviton. And in gravity, there's really just one type of charge. That is mass. Everything with mass, or from special relativity, equivalently energy, everything gravitates in the same way. Everything is sort of pulled together by gravity. Now, electromagnetism, which we've been magnetism, this has both positive, two types. It has both positive and negative charges. And we've seen that like charges repel each other. The two electrons are pushed apart by the electromagnetic force, but opposite charges attract in electromagnetism. This is why how we have the bound state of the hydrogen atom. But in fact, to understand the strong nuclear force, a theory known as quantum chromodynamics, what should I write? Chromodynamics, I suppose. So the title and the language I'm going to use comes from an analogy with, thinking about color, chromo, just as a way to visualize things. But in chromodynamics, there are in fact three types of charges, which are given, the language that people use to talk about this, because we can no longer just talk about positive and negative numbers, is we think about three sorts of color charges: green, blue, and red. And I've switched from actual red to pink, which hopefully shows up slightly better than it did last time. So in chromodynamics, there are actually three types of charges. So the interactions we can no longer understand in this very simple classical way that we could with electromagnetism. But indeed, these components of the proton and the neutron, we call them quarks, and they come in three different colors. And just like the photon, exchanges of the photon mediated the interaction which gives rise to the electromagnetic force. It tells charges how to repel or attract each other. Quarks interact via the exchange of a different type of massless spin-1 bosonic particle known as the gluon. And these gluons, in fact there are 8 of them in the full quantum field theory description, they carry this chromodynamic force between quarks, which just like the photon, tells them how to repel or attract or more generally interact. Good. So let me, great. So what actually is the proton in this description? Well, we come to a new sort of phenomenon which exists in these more general quantum gauge field theories, which is known as confinement. And I'm going to tell the story today a little bit out of historical order. This is something that took us a very long time to understand how to properly account for in the framework of quantum field theory. There were some deep puzzles there. It wasn't until the 1970s or so that we really understood these sorts of theories. But what happens is there's a new phenomenon where, just like we had multiple sorts of, we have a more complicated structure of charges, the bosons, the gluons, which carry these charges in this more general gauge theory case, are themselves color charged. previously for the previously the interaction, all these colors, the interaction of electromagnetism. If you have an electron and a positron and they come together, well, their charges to annihilate to a photon, their charges have canceled out, and so the photon has zero charge. But that's not the case for chromodynamics. If you have two quarks, am I going to get myself into trouble with this analogy? Maybe. If you have two quarks, in fact, you don't just have charges that add up to zero, but the gluon carries sort of two kinds of charges, and this, well, it's a gluon. Okay, and this leads to the fact that gluons can scatter among themselves. Quantum electrodynamics is, well, physicists, mathematicians would say it's a linear theory. The photons interact with the charged particles, but the photons don't interact with themselves. But quantum chromodynamics is much more complex because the particles that carry the force are also charged under that force, and so they can interact with themselves. And so you have new sorts of phenomena, and in particular, the strength of the gluonic interaction, the QCD interaction, has a curious property that it grows as you go to longer distances. Let me first say, okay, so hydrogen, we had a positively charged proton and a negatively charged electron, and they came together in this neutral bound state, right? Well, one positive and one negative charge, so overall things are neutral. How do you have a neutral sort of bound state in QCD when you have these three colors? Well, it's not perhaps immediately obvious, but in fact, one way in which you can end up with a totally uncolored bound state is to have three quarks, each of which is a different color. So the proton and the neutron each have three quarks. For the proton, it's two of what are called up quarks and one down quark. For the neutron, it's one up and two down. This explains their different electromagnetic charges, the fact that they have different kinds of quarks, but they each have one red, one green, and one blue, and so you can think about together all three colors adding up to something like white, uncolored, uncharged under the color force. And the pions, which we saw as carrying this Yukawa force that hold the nucleon together, the nucleus together, pions consist of one quark and one anti-quark. And I've drawn the anti-quark in purple because just like there are anti-particles, there are anti-charges as well. You can think of, well, whatever sort of color you think is the anti of green. So you have two different sorts of ways to all add up to an uncolored, uncharged particle, either by having one of everything or one color and its anti-color. And the way you should think of, there's another one, good. The way you should think, so we talked about the photon carries this electromagnetic force. In the quantum mechanical description, the electromagnetic force between the components is strong enough that it gives sort of it leads to bound states. We talked about the analogy with thinking about a particle in a box, and that's something of an analogy for the hydrogen atom, although really in that case you have a potential, what tells you how strongly the particles interact, which is strong enough to give some bound states behavior. We talked about there being then sort of a discrete number of energy levels. Fine. But we've also talked about that if you shoot energetic enough photons at hydrogen or at some metal, whatever sort of atom you like, then you can ionize it. You can get to a situation where the proton and the electron are really arbitrarily far apart, right? You separate them. So it's not exactly like they're in some box and they really are confined to interact with each other. But that is the case for QCD because it has this funny quantum mechanical behavior of the strength of the interaction getting stronger as you go to long distances. You can think, I think a good thing to think about is if I have, say, this pion with one up quark and one anti-up quark, and just like hydrogen, they're held together by exchanging lots of gluons. I'm not going to properly account for color in this picture, but you should think there's some force between them. They're being held together by exchanging gluons. Now, the strength of this force is so great that if I try pulling apart my up and anti-up particles, it takes so much energy to pull these things apart. The quark and the anti-quark of a pion, for example, it takes so much energy to pull them apart that before too long, they don't just snap apart and fly away freely. There isn't an ionization process. But before long, there's so much energy in these gluons that are holding them together that you actually pop out another pair of quark and anti-quark out of the vacuum. This still conserves color or electric charge, everything you might want. I'm creating a particle-antiparticle pair. But the point is that this gluonic force is so strong that at long distances, we can never see any particles that carry the color charge. They're all bound up, confined into particles like protons, like pions, that have net zero color charge, unlike the case of electromagnetism. This really is a fundamentally different and inherently quantum mechanical sort of phenomenon that, as I said a few minutes ago, really did require us to deeply understand the framework of quantum field theory to accurately describe.
Here you have two quarks. You try to pull apart.
Yes.
And you get 4 quarks.
Indeed.
So they are smaller quarks and bigger quarks?
No, what I'm imagining, these are all the same sort of quarks. So this is, again, an up, well, you could have different things. What do I want to say? What I'm describing here is that you can think, good. You can think both as an analogy and also at some deep level as the up and anti-up quark here in the pion being held together by strings, more or less. And so when I or rubber band, perhaps might be a better analogy. And if I try to pull them apart, I have to put in so much energy that then, that the energy I input into the system, before too long, the energy required to pull them apart is greater than, let's say, twice the mass of one of these quarks times c squared. So by special relativity, that means that you can have a process which exchanges that potential energy in the gluons for the creation of a quark and an antiquark.
So in this case, the energy that you give them is converted to quarks?
That's right. Indeed. The question is about, yeah, good. So indeed, the statement is that the energy that you try to put in to separating quarks from each other, because QCD is so strongly bound, because that takes so much energy, that energy gets converted into creating new quarks out of the vacuum. And that's how everything stays in some combinations that in total add up to what? Or add up to not having any color. Yeah. Good. Great questions.
Oh, sir. Is that violating Einstein's rule of E equals? I mean, are you creating energy?
No.
The energy that's created when you separate them apart greater than it was there in the beginning. That's what. Seems like that. What it
well, good. Indeed. So I'm imagining. I'm not thinking now of looking at a pion that's sort of isolated on its own. I'm thinking of adding energy to the system. Maybe you shine like a really powerful laser or something. Or I mean, you can imagine sort of going in and grabbing that you can't do that at a microscopic scale. But no, and energy should still be conserved. If you put in more energy than just the energy it takes to create these quarks, then they'll end up with some kinetic energy as well. And so when this rubber band snaps, they'll sort of fly. You'll have two pions now that will fly apart with some energy.
So
let me. How about we continue this later on? I should really get on. We need to get to. I'm sure people will be very upset if I don't actually get to the Higgs today. So good. So now we have a proper accounting, in some sense now, of all of the particles that make up, that exist stably, say, in our bodies. We've seen the up and the down quarks together in these combinations because of these bosons called gluons are confined into protons and neutrons and pions. We have the electrons. Of course, the electrons, together with the protons and neutrons, make up all of the atoms in our body through this electromagnetic force. And we observed also we have these neutrinos that appear whenever you have, say, weak nuclear decays. You can have neutrons that decay into protons, electrons, and neutrinos. And in some sense, this, as I said, this is an accounting of all of the particles that exist stably in our bodies. And it was a great surprise to physicists in the 30s originally that this is not all that exists. So there were these physicists, Nettermeyer and Anderson. They were, I think that they might have been really astrophysicists, high energy astrophysicists. And what was realized around this time is that just like I've talked about us having neutrinos from the sun, for example, always passing through our bodies, coming to us from Earth, and of course we have photons from the sun and other stars that reach us. In fact, there are lots of quite energetic particles that are incident upon the Earth from all of these sorts of very high energy astrophysical events that have taken place in the past billions of years. Things like supernovae, neutron stars, black holes, plasmas, all of these things that can create very energetic charged particles, those are all out there in space, and many of them, or some of them, hit the Earth and come in, hit the atmosphere, interact in the atmosphere, and produce sort of, it's essentially like a sort of particle collider that is already out there for us to examine. You have very high energy particles that come in and hit the atmosphere and produce lots of other particles. And by examining this, they found a surprise. There's a particle with the same charge as the electron, but for some reason, which is much heavier. I forget. This came to be called, I should say, the muon. It has the exact same charges as the electron, so it interacts with photons and things in the exact same way, but it's something like 200 times heavier. And really, this was a great surprise to physicists at the time. There's a great quote, which I forgot to add on here, by a physicist, Isidore Rabi, I believe. Around this time, he said, "Who ordered that?" Indeed, it seems like we understand the stuff that makes us up. It is remarkable that there is more than that. There is, for some reason, this additional heavier cousin of the electron. Good, because it has the same charges as the electron, but is heavier, it's allowed to decay. It's not stable like the electron is, but it's allowed to decay into the electron and into some neutrinos. And so these particles are only very short-lived, something like a microsecond in their rest frame.
I understood it.
Good. And not only that, okay, so we can go back to our colliders, and we talked about electron-positron annihilation, and I think in the diagram I drew before, we had electron-positron annihilating into a photon, which then goes back to produce an electron and positron. But in fact, there are the same sorts of interactions for any charged particle. Any charged particle can annihilate against its antiparticle, or by sort of time reversal, because physics is invariant under roughly things changing from forward and backward in time. For any charged particle, you can have a photon produce a charged particle and its antiparticle. So soon after we discovered the muon in cosmic rays, in these very high energy events that nature has provided for us coming from the atmosphere, we went to we built colliders where you collide electrons and positrons, and found that you could produce muons and antimuons. And that must be true because they have the same sorts of charges as the electrons. But not just that, you can also produce all of the charged particles of quantum chromodynamics, all of the charged particles of quantum chromodynamics. You have these processes, for example, for protons and antiprotons. But also, well, you can produce the excited versions of protons and things that we've talked about. But it turns out that there's even more to be discovered. Again, a great surprise when physicists went and collided positrons and electrons, sort of transferring all of their mass into the energy of the photon and seeing what came out the other side. There were, in fact, lots of new, physicists call them resonances, lots of new particles to find. Each of these places where, again here you're sort of looking at how many of these interactions happen for a given number of protons and electrons interacting with each other. And each of these big bumps corresponds to producing a new sort of particle, which told us that not only are there these extra heavy cousins of electrons and heavy cousins of neutrinos, but in fact there is also a multiplicity of versions of the quarks. And in fact, what have I got? Yeah, good. So in fact, historically, this is one of the big reasons why physicists fell in love with group theory as a mathematical field. It seemed like I had on this slide, and this isn't even all, this is only one way of looking for new particles, but even just with this, there are all of these new states. People refer to it as sort of a hadronic zoo of particles. It seemed like, again, we were back in the era of there being tons of different things and seemingly no relation between them, but in fact, we could understand, based on symmetries, that these particles were in fact all related to each other, and that the description, understanding how they were related to each other, these both the neutron and the proton that we know and love, and also some heavier cousins, required the introduction or required understanding that there were also additional quarks in addition to our up and down quarks that make up the proton. And so this, trying to understand what things look like in the hadronic sector, led to physicists building bigger and bigger colliders, using very high magnetic fields to accelerate charged particles to absolutely enormous speeds. For the LHC, the protons, the Large Hadron Collider, the current biggest collider, which is at CERN in Geneva, the protons travel at something like 99.9999991% of the speed of light, 186 miles per second. And as a result, these protons have enormous energies, and from special relativity, like we've been talking about, that means that their collisions can produce very massive particles. I should put this down. Oh, good. Yeah. So the picture. This is tracing out the ring of magnets that comprise the Large Hadron Collider. This is on the border of Switzerland and France in Geneva. Here's a close-up of a physicist, engineer working on these superconducting magnets that allow charged particles to be accelerated up to absolutely enormous energies. Here is, and the resolution isn't as nice as I'd like, this is the CMS detector. There's a person for its scale you might be able to see down here. This is when they have it sort of open to work on it. When it's in use, these two sides are pushed together. I highly recommend, if you ever find yourself in Switzerland, I highly recommend trying to get a tour of one of these detectors. It was, for me, it was absolutely a sort of spiritual experience seeing this. Really, I mean, these are pinnacles of human achievement. These absolutely enormous machines that allow us to do amazing physics and learn about the world at very small scales. So I highly recommend if you have the chance to visit. Good, but we go and
This is how the boson particle was created?
indeed, yeah, so we'll get to the Higgs in a moment. The Large Hadron Collider is where the Higgs was discovered, that's right. But before the Higgs, we're still discovering the quarks. We find not only is there one extra version of all of our familiar particles, in fact there are two. In total, there are 3 generations of sort of fundamental matter that make up the fermions of the Standard Model.
Fermion.
Indeed. The stuff that is stable, the stuff that exists in our body, are these lightest versions, this lightest generation or family, the up and down quarks in our protons and neutrons, and the electron and its neutrino cousin. But there are, in fact, two more copies of all of these fundamental particles. The electron has the muon and also the tau. The quarks, we started with somewhat sensible names, up and down. Somehow, for historical reasons, the heavier versions, the charm and strange in the second generation, and the top and bottom, also heavier versions of the quarks, which, just like we saw the muon being unstable to the electron, to decaying into an electron, the heavier quarks are also unstable to decaying into the lightest ones. And in fact, this picture of 3 generations of fundamental matter was experimentally completed only in 1995. In fact, at Fermilab, nearby, an hour away, they had this, what was the leading collider for many years called the Tethertron, where they collided, I believe, protons and antiprotons, and they discovered the top quark in 1995, to give you a sense of why it took so long, the up and down quarks, as we said, make up the proton. The top quark, as this fundamental particle, which is a cousin of the up quark, one top quark, this fundamental particle, all by itself, has a mass of more than 170 protons. So these, for some reason that I can talk later, we don't fully understand, why, for some fundamental reason, we have this copying of all of our matter, or why there is this enormous hierarchy in terms of the masses. It's not, they're not, 3 versions that are all at approximately the same mass. There really is a humongous hierarchy of masses as you go from one generation to the next. And indeed, the top quark, the heaviest quark, really the heaviest fundamental particle we've discovered, is hundreds of the mass of the proton.
Does this exist in nature, the top quark?
Indeed.
Is it a part of an element that we know, like iron?
Good. So let me repeat that all of the only stable particles belong to this first generation. So the only things that exist in some fixed quantity in this table or in your body are these first generation quarks. Certainly these other ones are part of nature, and you can, they'll play a role in the very early universe, which we'll get to starting next week when everything is very hot. But they don't exist, because they are unstable and they can decay to these lighter versions. They don't exist in matter, the way you might think about a solid or something like that. Yeah, quick question. Yeah.
How do we know that it is just one particle and not a bunch of protons together?
How do we know that it's one particle
How
and not
do we
a
know
bunch?
that the top is just one particle called top and not a bunch of protons together interacting with each other? How do
Good.
find that?
Based on how they decay. I mean, a bunch of protons together. Good. Sorry. The question, to repeat, is how we understand experimentally that something like this is a single particle rather than just being a collection of a bunch of different protons or something. A collection of a bunch of different protons have this electromagnetic charge. So trying to just collect a bunch of protons, they would sort of blow apart. But the way to understand, well, good, maybe a slightly more refined question is maybe you might think the top quark is actually a super heavy nucleus. Like one of the, I mean, well, you might ask that question, but the way that we detect these particles is from their decays. Yeah, good. What do I want to say? Well, maybe electron neutrino. Yeah, good. So when we produce one of these very heavy particles in a collider, we observe it to decay into some of these lighter particles. If you were to produce some very heavy element, I mean, good. We have nuclear physicists trying to produce some of these very heavy elements all of the time, and these sort of dissociate into smaller collections of neutrons and protons. But it's not just that we somehow measure the mass. It's not just that you get the information about mass somehow. We're really measuring the decay of these particles into other fundamental particles. And I should say the production of them happens also via some fundamental process. It's a good question, and maybe we can talk more later. Let me move on, because, right, good. So there's one, we have the three generations of matter. There's one more sort of physical phenomenon that we saw and we haven't really explained. We saw these weak nuclear decays last week, that you can have a neutron which converts into a proton and spits out an electron and a neutrino. But we just sort of added that from Fermi as some new sort of interaction. And similarly, the decay of a muon into an electron and some neutrinos. But the other interactions we've talked about, the electromagnetic interaction, the strong nuclear interaction, are carried by these massless spin-1 bosons, the photon and the gluon. Whereas it seems somehow this is different. And again, exploring in colliders, we found that when you go to when you can look at very small distance scales, in fact, there is a spin-1 boson responsible for these weak nuclear effects, but it's a massive spin-1 boson called a W boson. And this is puzzling in a sense. The masslessness of the photon and the gluon, the fact that they can mediate these forces, is very tied to, is part and parcel with a certain symmetry that exists for these particles. That's both the reason why they have zero mass and explains which sorts of interactions they have. And it was confusing for many years to find that we needed to account for these spin-1 bosons that were somehow massive. And the fact that they're very massive explains why they have sort of more subtle effects than the photon. They also are unstable. They don't exist in matter or anything. They only exist for very short periods of time where basically from quantum uncertainty they can pop into existence and cause some transition like this. And so the answer came in, good, the answer to understand how these vector bosons, these spin-1 bosons, could be massive, despite what you think is a symmetry that protects their mass, that makes them massless, is to have some sort of symmetry breaking. So
shouldn't they be classified separate from the other quarks that are stable and are part of the protons and the neutrons? And why calling them cores of the same thing when they really are not? Some of them are stable and exist in nature, and some of them that don't. So why do we say, we put them together and we try to tell
Yeah.
people that they are the same?
Good. Okay, let me, I think we should continue this at the end because I want to get on to the Higgs mechanism. But you can understand very precisely that these have all of the same properties in terms of a quantum field theoretic description, except for their mass. So indeed, there's something, I'm not trying to hide something, there's something different. It's certainly true that we're only made out of these very lightest, these stable things, but in terms of which sort of interactions the particles have, these heavier versions really are heavy copies, but it's the fact that they have extra mass, which means that they can decay into these lighter versions. But let's talk about that a bit more at the end. Good. So we need to do some spontaneous symmetry break-in. Maybe I won't talk about the example of a magnet for time. But what you can think about is a ball on a hill. Imagine I have a hill. Good. Maybe even before that picture, I could have started thinking about a ball in a spherically or circularly symmetric sort of potential, just sitting at the bottom, some very simple potential or valley like this, and of course there is a circular symmetry here. It looks the same no matter which way you look, or it's unchanged by rotations. Now here, if the ball is at the top of the hill, then again, it sees the full rotational symmetry of this potential, right? For this ball, everything looks the same in each way. If you rotate it, things look the same. But just intuitively, you know that this is sort of an unstable configuration. Even though you have a spherical symmetry, if you start the ball off at the top of the hill, what will happen is there will be some spontaneous symmetry breaking. And from some very small, well, if you're thinking about a ball, from some fluctuations, from some not being placed right at the center, what have you, it will spontaneously fall down the hill in some given direction. And even though the hill continues to have this, your background continues to have the rotational symmetry, because of this spontaneous symmetry breaking, your ball is no longer at the symmetric point of this potential, but instead, locally, it sees some violation of this, some spontaneous breaking of this symmetry. Okay, and this, in fact, it really is what happens with the Higgs field. The Higgs is so the Higgs boson, the Higgs field is a scalar spin zero sort of field that was introduced to try to understand how the W bosons could be massive. And indeed, the Higgs we haven't talked about cosmology yet, we'll get there. The Higgs starts off, in a sense, at the origin of some field space. It starts off just like we talked about all of our quantum fields, electrons, photons, what have you. They have some fields that exist throughout all of space and time. The Higgs also begins with zero value throughout all of space, just like all of our other fields. But this spontaneous symmetry breaking happens, and physicists use the term condensation. You should think of, what produces dew outside in the morning. Dew comes from, during the day, we have some water vapor that exists in gaseous form in the atmosphere, and at night, when the air cools down, some of that water vapor condenses into the liquid form of water, of dew that you see on surfaces in the morning. And indeed, something very analogous happens in the early universe with the Higgs. In the very early universe, due to thermal effects, because it's very hot, the Higgs is trapped at the top of this potential. But and with zero sort of background value, just like the rest of the quantum fields in our universe. But when you cool the universe down, when it expands and cools, you have, again, a condensation effect where where the Higgs rolls down as a field, rolls down its potential, and finds itself at some place that is displaced from the origin. And so, unlike all of our other sort of quantum fields, which if you look in vacuum, in empty space, they have zero value on average, and you know, particle physics is about studying the excitations, the photons or the electrons, what have you. The Higgs is somewhat different because it has been pushed away from the origin, pushed away from having zero field value everywhere, and actually has a non-zero field value. There is some background, non-trivial Higgs field permeating all of space. And indeed, this is what allows for all of the particles that we've been talking about to gain mass. The analogy that people commonly give is if you think about if you think about attending a dinner party and having an empty dinner party versus one that is full of lots of guests, and you're trying to move from one room to another, perhaps, when your dinner party is full of many people, then you have to take a slightly, you might have to interact with them, horribly, to get from one place to another. And indeed, this works as an analogy. There is some sense in which it's true at a deeper level. The particles that interact with the Higgs, in this phase of the universe where the Higgs gets some non-zero, when we say vacuum expectation value, the Higgs field is non-trivially everywhere around us, then particles to travel, to move, particles which interact with the Higgs, which are all of the particles that we see as having mass, have to sort of get through this Higgs field. And that requires them interact, in a sense, with the background. And this is the microphysical effect that gives mass to, the massive particles that we see. Good. And, let me quickly... So indeed, we have to build these enormous colliders to see this very high energy, small distance physics. Here are some fantastic plots. Good, we discovered the Higgs at the Large Hadron Collider. These are some plots from one of the experimental collaborations, ATLAS, at the Large Hadron Collider, showing, as they ran their experiment, the buildup of the sort of events. Again here, just like I talked about there, what you're looking for are the particles to which the Higgs decayed. So these are looking at two different ways they can decay. This decays into 2 photons, and they're looking for this small bump here that indicates that there was something extra happening at that mass, which is exactly the mass. I mean, this is how we measured the mass of the Higgs, that we found that there was some extra effect that was causing 2 photon decays in our detector that we interpret as the Higgs boson being produced, and indeed it was exactly where we thought it would be, exactly the right sort of interactions. This is a different sort, these are different, just to get across, experimentalists have to be very careful. They care a lot about different backgrounds. As you can imagine, they're looking for very subtle effects, so you have to account very carefully for what sort of other effects there might be that look somewhat like the thing that you're looking for, and they do this accounting very carefully. And indeed, back in 2012, we were able to discover the Higgs boson from the fantastic work of experimentalists
The
at the
Higgs
LHC.
boson was discovered only in this collider experiment. Was it over discovered in any other physics phenomena?
Indeed. So the question is what sort of experimental information we have about the Higgs. Indeed, we needed to build the Large Hadron Collider, and what they do, and indeed that's the only place that we've been able to observe the production of Higgs bosons directly. What the experimentalists do, which I think is a great practice, is that whenever you have an enormous collider like this, for financial reasons, we can only build one Large Hadron Collider, but there are even more than two, but at least two entirely separate experimental groups that don't talk to each other. I showed the detector I showed was of CMS, the compact muon solenoid. Those plots I was showing were from Atlas, and I forget.
My question is there any other physics phenomenon other than colliding that showed Higgs particle exist?
Indeed. In order to produce Higgs bosons that we can study, we needed to build these colliders. So until we build other sorts of colliders, which if you have a few $1 billion to spare, I'd love to talk to you. Or until there are some ways, maybe when we get to cosmology, there will be some ways to see some evidence of the Higgs boson in the future in cosmology. But for now, it's just colliders. Let me get through the last couple slides, because I don't want to. If people have things to go to, I don't want to. Okay, but look, we have. I've built up for you the standard model. We have these three generations of matter, the ones that make us up, these heavier ones that are unstable, as we've been talking about. We understand these force carriers. The Z boson is related to the W boson in the electroweak force, the photon, and the gluon. And the Higgs boson was, in some sense, the missing piece of the puzzle there. And I want to, again, emphasize that we have this remarkable picture of looking at what matter looks like on smaller and smaller scales, and being able to understand at every step of the way what the constituents of matter are, how they interact, what the physics is that describes all of these phenomena we see. And we can really go sort of the other way and understand how the physics at these very small scales, how the exchanges of W bosons, how the gluons and quarks inside the neutron lead to these longer distance physical phenomena of having nuclei, of having atoms and molecules and such. We can understand how all of these things come to be from their more fundamental components. And I want to show this slide I had made a few weeks ago for a more technical talk I gave at Aspen. This is so I showed the standard model just as a listing of the sort of particles that we have. This is the standard model written as a quantum field theory. This is, well, what I've written here is an object known as the partition function of the theory, and we can describe the Standard Model in a very simple, compact way, using the language of quantum field theory. This describes the particles that exist, are different fermions, and how they interact with the Higgs field to get masses, are different sorts of gauge bosons, the Higgs. I've even included gravity here. We'll get to that next week. I want to show some symbology, because it's not just vague words about what these particles are. If there's any confusion in what I'm saying, it's my fault. The math here is precise. We can understand precisely from this object, the partition function of the Standard Model written as a quantum field theory, we can understand precisely how these particles interact, what sort of bound states they form, what sort of physical phenomena we can understand. And I also want to emphasize, this is not a point in addition to the structure of the Standard Model, what sort of particles there are, in order to make precise mathematical predictions, we need some values for certain things in, it's not just what types of particles exist, but things like what the strength of our different interactions are, or how various particles couple to the Higgs precisely to get the masses that they have. And this is really an incredibly simple parsimonious theory. We have something like 24 of these parameters, 24 of these numbers, which have to be supplied, these free parameters, which really describe all of the matter that we know, all of the matter we're created out of, and also anything that we've seen in the lab, in colliders, out in the universe. So it's a really remarkable theory that allows you to describe a huge amount of information with very few fundamental free parameters. And furthermore, and we'll go into this more in the last lecture, this series, this isn't the end. The Standard Model, those particles I've written down, in some sense it's complete, it's entirely internally consistent, but we know that there are additional effects that aren't covered, that aren't included in this description of nature. We need to do things like provide masses for neutrinos, we need dark matter, and there are many things. Even though the Standard Model is a remarkably simple theory in some sense, there are still further questions you could ask about. Why do the gauge couplings have the values that they have? Why do the masses have the values that they have? And a very interesting thing to think about is if there is some even deeper fundamental theory that really explains those parameters rather than putting them in. And this is just a summary plot from one of the experimental groups at CERN. They do, this is only a very small fraction, they do tons and tons of ingenious searches for exotic types of particles, other sorts of physical phenomena. We're looking very hard for what might be beyond the Standard Model, and so far haven't seen anything at colliders. But we know that there is more out there to be discovered. Great. This is the end of the first half, in which I've tried to zoom down from human scales all the way to the smallest scales we yet understand. I hope I've been able to convey some picture of what I see as the beauty in this sort of description, in being able to understand nature at its most fundamental scales and understand how these remarkable emergent phenomena that we see in our everyday lives really appear. Starting next week, we're going to switch course to talking about cosmology. I know that there have been questions about gravity. We'll finally get there, and we'll see how really, well, one of the reasons I'm talking about this intersection of topics is because remarkably, these fundamental details of particle physics that we've been talking about, that indeed today we need to build enormous colliders in order to understand anything about. But in the early universe, these fundamental details of particle physics at small scales are actually going to become relevant to control the large-scale evolution of the universe. So I think there'll be lots of fun things to see in the next few lectures, and I look forward to seeing you there. Thank you. There were some questions from before, yes.
Yeah, I wanted to ask, have they seen anything in the cosmic rays where you get similar energies? Is there enough data in cosmic ray?
That's an interesting question. We haven't. Good. You know, I don't know what the fundamental answer there is. Indeed, cosmic rays have enormously high energies.
That you have no control over.
That's precisely the point. That we needed to build these fantastic colliders, and also we needed fantastic experimental physicists who could really understand very precisely what the rates were, what they should be, all of these sorts of possible background signals that aren't quite what you're looking for and you don't want to confuse with your signal. I don't know at what rate Higgs bosons might be produced from cosmic rays. That would be an interesting thing to know. It probably is the case that just because we don't have very much control there, it would be very hard to say anything definite. I think there had been one in the back, maybe, that I didn't, yes?
That was a singular question, whether or not stellar events can produce the same type of phenomenon that these two gentlemen, whether or not Higgs bosons could be created naturally.
Yeah. Well, I'd say even at the LHC they are being created naturally, but I understand what you mean. Probably not. Yeah, stellar events. Stellar astrophysics gets us some of these heavier things. You produce muons, you produce these exotic neutrinos, and some of these heavier quarks. But even the energies seen in things like supernovae don't get you very large compared to some of these heavier quarks or the Higgs boson. There's a possibility that, probably the best chance for some really separate sort of detection of these physical phenomena is gravitational waves. We've seen gravitational waves from black holes. A very interesting pursuit that many people are thinking about, both on the theory and experiment side, is to discover sort of relic gravitational waves from the very early universe. Even earlier than, as we'll see next time, we can probe with photons and neutrinos and things. You could hope that to still detect gravitational waves from very early on, and then you would be able to see in those some role of the Higgs boson there. That's an interesting question. Yes?
I just wanted to make a comment that the Higgs boson was actually discovered at Fermilab. And they gave the information to CERN so they knew exactly where to look.
Right.
And CERN used their data in their final statistics.
Yes. Yeah, indeed. It's an unfortunate accident of history. The Tevatron, this big collider at Fermilab, was scheduled to close down, and it had seen, but by the time it closed, it had seen some hints of the Higgs boson already. But physicists, were very concerned with making sure that there aren't any sorts of background events that could, or anything like that, that could masquerade as the signal we want. And so we only declare discovery once we have some very statistically sound detection we're 99.99999% sure that it really couldn't have been anything else. And so unfortunately, the Tevatron closed down a bit before it got quite to that threshold, and we only started the LHC. Yes?
The top person has such tremendously more mass.
Yes.
Should we be aware, that requires energy, correct?
It has energy.
Is this a thought at all? Should we be thinking about mass and energy?
Yeah, no.
To that?
Well, indeed, it requires a lot of energy. We have to build very large detectors and accelerate protons to very high energies in order to produce the top quark. It's not a very efficient sort of production. So I don't think there's any application for the energy industry or anything like that. But indeed, there's lots of mass there. Yes, this gentleman had his hand up.
Yes, you made, with the one graph there, it showed that they're searching for all kinds of new particles.
Uh-huh.
Is this gonna simplify a standard model or further complicate it so much we'll never figure it out?
It's a great question. Well, good. The way we should, I'd say the way we should approach these experimental searches is we need to just look for what is there. But indeed, it's a really good question. Many of the theoretical ideas have been about explaining some features of the standard model, and then if and when you find some of these particles, you might understand, for example, why the neutrinos are so light compared to the other particles. Or you might understand why the top quark is so heavy compared to the up quark. Some of these sorts of models that predict these particles tell you things about that. But indeed, it's possible. It's possible also that there's just other stuff that doesn't fit into the standard model, like dark matter. Right? Dark matter is some other thing. We know in some sense that it doesn't fit very nicely into the standard model, and yet is out there. So you shouldn't, it's a really interesting question, and I'm all for understanding very precisely, what sort of theory prior, what you might expect to see based on having that theory, that nature should have a beautiful sort of physics theory, but you don't want to, you want to just search for everything, and we'll have to see if it's beautiful or not from that. Yes?
Sounds good. I know, we're good.
Oh, good. Okay, wonderful. Yes, yeah.
Could you explain how physicists say that the universe consists of dark matter, and do we have any idea of what it might be?
We're gonna get so we're gonna get to cosmology next week. So let me give a longer answer then. We have many ideas about what dark matter could be, but we haven't. So far, we've only seen it interact gravitationally. So we haven't sort of uncovered its particle nature, what exactly it's made out of. But there are many ideas and many experiments that are going on. Yes.
Is there an understanding of why the proton seems to be stable while the neutron decays?
Thank you.
A beautiful, absolutely beautiful question.
Thank you.
Why does beta decay only occur in some nuclei?
Thank you.
Okay. I'm going to have to defer a bit on the second question, which is about the details of nuclear physics, which is a fantastic study, and there's some rich interplay of these different physical effects. But I'm definitely not a nuclear physicist, so I can't really speak to that. It's a very, it's a beautiful and very deep question about the proton. We know, good. What do I want to say? So it is the case that the up quark is slightly less massive than the down quark, and so the what do I want to write? The proton, I'm going to ignore the colors, but the proton consisting of two ups and one down has in fact a smaller mass than the neutron consisting of two down quarks and one up quark. So this is the reason We're coming back really to the up quark being lighter than the down quark. This is the reason that in vacuum, whoops, I did not write neutron. In vacuum, indeed, a neutron is unstable to decay into a proton. The proton is stable, as far as we've been able to tell. In fact, one of the very well-motivated ideas in physics beyond the standard model is the idea of gauge coupling unification, or grand unification. This is the idea that in the standard model, we see these three different types of forces, one carried by gluons, one carried by photons, one carried by these heavy W and Z bosons. And correspondingly, we have these three different gauge couplings that tell you the different strengths of these three sort of gauge interactions. Grand unification is the remarkable observation made in the 80s that you can have some very simple theories in which at high energies, these three different gauge groups all unify and come from the same fundamental force that at some very high energy is spontaneously broken, like the Higgs, and then at low energies, we see these three different sorts of avatars of what at very high energies, what at very short distances is a single sort of force. And, good, the reason I bring that up is because in those theories, a classic sort of the first most remarkable prediction of those theories was indeed that the proton would be unstable. That fundamentally, just trying to think of how much of this I can explain right now. Fundamentally, there are some extra heavy bosons, just like our spontaneous symmetry breaking in the standard model gives these heavy Z and W bosons. There are, in these grand unified theories, very, very heavy bosons called, very, very heavy bosons called X and Y bosons. And those lead, what do I want to do? Exchanges of those particles can lead to, well, good. Sorry, I'm struggling with what sort of diagram to draw, but what that leads to is the proton decaying into one of, for example, these pions and a photon or electron or something. And indeed, this is a classic prediction of grand unified theories. You will find...
is it possible that the neutron is neutral in charge?
Yes.
It does not interact
with the photon.
With anything else because it is neutral.
No.
In this case, it doesn't enter as much as the proton. The proton, because it has a charge, okay, so it make it possible for it to interact with other things.
No, the neutron, the difference in charges between the proton and the neutron is the electromagnetic charge. But they still interact via gluons, they still interact via W and Z bosons and these heavy things. But let me get back. There's a fantastic quotation, I believe from Annie Hall. Woody Allen's movie, chatting to a girl. He says something, have you heard the universe is decaying or something. There was a lot of popular press in the 80s about this prediction that the proton would decay, and physicists went and built these fantastic The point is that these are mediated by some very heavy bosons here. And so this happens very, very rarely. Just like the heavy mass of the W and Z led to weak processes that only happen relatively subtle effects, these very heavy effects from grand unification lead only to very rare proton decays. So what physicists did is they built these enormous detectors to look for such things, and to everyone's surprise, we have not yet. So this is an enormous. This is Super Kamiokande in Japan, a current iteration of one of these experiments that look for, the lighting is not great, but one of these experiments that look for proton decay, they need to, because it's such a rare process, you need to basically put some very pure water in an enormous tank. And these are some people in a boat servicing these detectors to give a sense of just how much water we're looking at. And it has been very surprising indeed that we have not yet found proton decay. In fact, this has been I've been inspired by that fact in my own research to think about whether maybe we should be rethinking, maybe there's some additional subtlety that we haven't appreciated in what physics looks like at very small distances. Because indeed this fantastic prediction of proton decay that we've been looking for very carefully hasn't yet appeared. So sorry to give such a lengthy quiz. It's a very good question. Yeah. Okay. Thanks very much.